Hello GATE aspirants, welcome to part 6 of GATE solid state physics series. Question number 30. The lattice parameters A, B, C of an orthorhombic crystal are related by A is equal to 2B is equal to 3C. In units of A, the interplanar spacing between the 1, 1, 0 plane is. So here A is equal to 2B, that means B is equal to A by 2 and C will be equal to A by 3. And the formula for this is interplanar spacing is D is equal to 1 upon under root h square by a square plus k square by b square plus l square by c square. Here HKL is 110. So D is equal to under root 1 upon 1 square plus 0 upon a square. Here B is a by 2, so this will be a square by 4. So this will be equal to D is equal to 1 upon under root 1 by a square plus 4 by a square, that is equal to 1 upon under root 5 by a square, that will be equal to D is equal to a by root 5, and 1 upon root 5 is 0.447 into a. So in terms of a, this will be the value. So answer is 0.447. And the answer range for this question was 0.445 to 0.450, and we are getting 0.447. Next question. In Hall effect experiment, the Hall voltage for an intrinsic semiconductor is negative. This is because, now this is Hall effect for semiconductors. And the formula for Hall coefficient RH is equal to P in bracket mu P square minus N in bracket mu N square upon E P mu P plus N mu N square. Here mu P and mu N are mobilities of holes and electrons, and P and N are concentration of charge carrier concentration of holes and electrons. Now for intrinsic semiconductor, N will be nearly equal to P. So N will be nearly equal to P. So here I can put N is equal to P. So from there we'll get RH is equal to, if we put N is equal to P, then this will be N in bracket mu P square minus mu N square upon N square in bracket this. So this will be 1 upon Ne in bracket, it will be mu P square minus mu N square upon mu P plus mu N bracket square. This is a square minus b square, which can be written as a plus b, a minus b, and it will cancel out with denominator a plus b. So RH is equal to 1 upon Ne, and in numerator we will get mu P minus mu N upon denominator mu P plus mu N. So this is the formula. But we know mobilities of electrons is greater than mobility of holes, so mu N is greater than mu P. That means this Hall coefficient RH is going to be less than 0, that is it will be negative. So option C is correct. Next question, 33. The energy dependence of the density of states for a two-dimensional non-relativistic electron gas is given by GE is equal to, now GK dk is equal to L by 2 pi the whole square into 2 pi k dk, and for spin degeneracy of electrons we have to multiply by 2. And for non-relativistic case, k is equal to twice me upon h cut square. That means dk is equal to under root twice m h cut square into 1 upon 2 root e into de. This will be value of dk. Substituting this in the first equation, ge de is equal to, this will be L square by 4 pi square into 2 pi into root of twice me h cut square into dk is root of twice m upon h cut square into 1 upon 2 root e into de into 2. This is the formula for GE. So this will be equal to L square by 2 pi in bracket twice m by h cut square into dE. So this is the GE part. So that means GE is not depending on E. That means GE is equal to some constant into e raised to 0. So value of n is equal to 0. This is the answer. Next question, 34. The dispersion relation for phonons in one-dimensional monoatomic Bravais lattice with lattice spacing A and consisting of ions of masses m is given by omega is equal to under root twice c by m in bracket 1 minus cos omega A 1 minus cos ka, where omega is the frequency of oscillation, k is the wave vector and c is the spring constant. For the long wavelength modes, that is lambda much greater than a, the ratio of the phase velocity to the group velocity is. Now omega is equal to 2c by m. 1 minus cos k can be written as 2 into sine square k by 2. So this 2 and 2 will be 4. That will be under root 4c by m into sine ka. Now in long wavelength region, k will tend to 0. And if k tends to 0, that means we can write sine k by 2, this is sine k by 2, is nearly equal to sine k. So sine theta is nearly equal to theta. This will be the case. That means omega is equal to under root 4c by m into ka by 2. So this root 4 and 2 will cancel out. So this will be under root c by m into ka. This is omega. Now phase velocity is equal to Vp is equal to omega by k. That will be equal to under root c by m into a. Similarly, group velocity we can calculate. It is Vg is equal to d omega by dk, and that will be again c by m into k. So that means Vg is equal to Vp. That means the ratio will be 1. So Vp is to Vg will be 1:1. So answer is 1. Next question. The binding energy per molecule of NaCl, lattice parameter 0.563 nanometer, is 7.95 electron volt. The repulsive term of the potential is of the form k upon r raised to 9, where k is a constant. The value of Madelung constant is. Now this is repulsive interaction. So for this repulsive interaction, delta U is equal to Na into B upon r raised to n, where this B is repulsion coefficient and Na is Avogadro's number, and this n is Born exponent, and its value will depend on the material that we are choosing. Now for solving this question, we will use Born-Landau equation. Born-Landau equation, and this equation is delta U is equal to Na into m, that is Madelung constant. Z plus is cation charge into Z minus is anion charge into E square upon 4 pi epsilon naught into R naught into 1 minus 1 by n. So from this equation it is NaCl. So Z plus will be 1 and Z minus will be 1. So this will be simply 1. And binding energy per molecule is given. That means delta U by Na is given to us, and that is 7.95 electron volt. This is given. This will be same. This will be Z minus, that is equal to 1. M is Madelung constant that we have to calculate. N is Born coefficient, and that is k upon r raised to 9. So n is equal to 9. And we need R as well. Now R is the separation between cation and anion, and here lattice parameter is given. So we choose R is equal to a by 2. That will be the separation between them. So that will be R. So these all values are known to us, we just have to substitute it. So we will get from here M is equal to, so this I will write delta U by NA is 7.95, so this will be 7.95 into E is equal to M, we have to calculate, Z is 1, this is 1, so into M into E square upon 4 pi epsilon naught into R naught is A by 2 into 1 minus 1 by N, so that will be 1 minus 1 by 9, and then we just have to solve it for M. So this will be, M will be equal to 1.7483. That will be its value. Up to 3 decimal places we have to write. So this will be 1.748. 1.748 will be the answer. Next question. Given that the Fermi energy of gold is 5.55 electron volt, the number density of electrons is, here EF is given, EF is equal to 5.54 electron volt, and that is equal to H cross square by twice M into 3 pi square into N raised to 2 by 3. This is the formula. Now from here we have to calculate N. So this will be twice M EF upon H cut square, that will be equal to 3 pi square N raised to 2 by 3. So here take 3 by 2, that will be equal to 3 pi square into N. So from here N is equal to 1 upon 3 pi square into 2 pi EF upon H cut square whole raised to 3 by 2. All of the values are given to us. So N is equal to 1 upon 3 pi square into 2 pi into EF is equal to 5.54 in electron volt. So multiply by 1.6 into 10 to the power minus 19 upon H cut square. So that will be, H is 6.626 into 10 to the power minus 24 the whole square upon 4 pi square. So into we will have 4 pi square, this whole thing raised to 3 by 2. So after solving this you will get N, and N comes out to be 5.911 into 10 to the power 28 per meter cube. So we have to round it off to 1 decimal place. So this will be, N will be 5.9. And the answer range for this was 5.9 to 6.0. So this is 5.9. Next question. Which one of the following represents the electron occupancy for a superconductor in its normal and superconducting state? Now for normal state, the graph of Fermi energy, Fermi function versus E, it looks like this. For temperature is equal to 0 Kelvin, and when temperature is greater than this temperature, then half of the energy levels up to Fermi level will be filled completely, and later this graph will look like this. This is for T greater than 0 Kelvin. So for general case this will be the graph. So this is wrong, this can be correct. And for superconducting state, if the material converts into superconductor, then electrons near the Fermi level, they make Cooper pairs, and Cooper pairs can transfer energy easily. So in that case the graph will look like this, not like this. So B is the correct option. So these were all the questions from GATE 2015 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.